It's a third topic of today. Let's consider impact loading problem. So in this impact loading problem, we have given a projectile with mass m with initial velocity v0, and we are asked to obtain the maximum stress sigma. Of course, the we don't consider 100% of the dynamic effect. Actually, if you hit the end of this bar, from the end, we assume that the stress is propagated through the entire body immediately. However, that's actually not true. When you hit like one side of the beam, actually you're gonna see that an elastic wave propagates. However, we are not considering dynamics seriously in our solid mechanics course because we are not studying dynamics, right? So you will just assume that as soon as this guy hit to this bar, the stress becomes uniform over the entire volume, even though it's not true. It will be a good approximation for relatively slow impact problem. So for this simple problem, we can do quite we can obtain the solution quite easily. If kinetic energy converted to 100% strain energy, then we're gonna have maximum normal stress. Then by equating kinetic energy and the strain energy, and noting that the the normal stress is uniform over the entire beam, we can say that it's V times sigma m square over 2e. Then you can obtain sigma m in terms of initial velocity and mass and Young's modulus and volume of the bar. Okay, now let's move on to a little bit more complex problem. So here the total length is given as L. We have 1 over L here, 1 over L here. We have 4A cross-sectional area and A cross-sectional area, and we are asked to obtain the maximum sigma here. And what you can also realize is that the normal stress N should be equal to the entire beam due to the force action reaction law. So what you can realize is that N should be same as 4A times sigma left, which is, let's call this as sigma left, and it should be also same as A times sigma right. This is right part. So what you can see here is sigma right must be 4 times sigma L. Okay, and by memorizing this and solve the problem, the maximum stress occurs when the entire kinetic energy converted to strain energy. So strain energy have this left part and right part. On the left part, we have 4a times half L. Half L is the length, and 4a is the cross section. This is the air volume for left volume. This is the volume for right region, and the sigma is given as sigma over 4 square because we have to consider smaller normal stress here, and we have sigma square over 2e for right side volume. So after summing up these two terms, left side term and right side term, you have 5 over 16 a and sigma m square over e. Then you can obtain the expression for sigma m quite easily. Now let's move on to third problem. When you have a mass and the gravitational acceleration g, suppose that the weight of this guy is mg, and when L over h, the aspect ratio is larger than 10, obtain the maximum normal stress for the beam. So in this problem, of course this maximum occurs when entire kinetic energy changes to strain energy. So we have to split this problem into two parts. First part, this guy dropped h, then from gravitation energy becomes kinetic energy, WH becomes to be 1 over 2 mv0 square, and this kinetic energy is converted to strain energy at maximum normal stress occurs. So if you equating that half mv0 square with the strain energy, so because this guy said that L over h is larger than 10, you can approximate that U is equals to be U sigma, which is P square L square over 6EI. Then what you can realize is the maximum force here occurs in terms of 6EI WH L cube. Okay, now here what you can realize is that maximum moment can be written as L times P here. So this is where maximum moment occur. This is where we have m equals 0 and m changes linearly over the beam. Yeah, I will not gonna solve for m as a function of x because we have solved this problem so many times. Okay, so after identifying m at the right end, which is the maximum moment point, yeah, you can write down maximum normal stress out of this maximum moment, which gonna given in terms of initial weight and height and c square and I and L and E. Okay, so this is how you can obtain the maximum normal stress for this problem. Of course, if you make this problem really accurate, in addition to H, you have H plus delta, slightly more deflection to obtain more deflections. However, it depends on the problem. If this problem, considered really heavy weight WMG, and if this WMG is much really large compared to the stiffness of this cantilever beam, you have to consider the contribution of delta. However, if you consider relatively small weight, you may not need to consider the effect of this little delta because the deflection will be really small. Okay, but it depends on you. So in this setting, today's solution, I skipped the contribution of this additional change in position along the vertical direction, but maybe some problem ask you how to incorporate the contribution of this additional gravitation energy change, and you have to think about how you can incorporate this, okay, for fun. Okay, so with that I can finalize today's lecture. So to give you overall summary of today's lecture, we first learn about the definition of strain energy and strain energy density. We then move on to a little bit more complex situation of general stress state. We learned that strain energy density should not be dependent on the coordinate. And second, we also learned that strain energy density can be decomposed into normal stress component and volumetric component and deviation component, like a UV component and UD component, which associated with volume change and the shape change respectively. And then we considered the impact loading problem and the energy conservation method for solving maximum deflection or maximum stress on the beam or structure under dynamic loading. Okay, so these are the topics we covered today's lecture, and in the next lecture we'll discuss about energy method of solving deflection, from this partial differentiation method. Okay, so with that, let me finish today's lecture and see you in the next lecture.